Yeah, hi.
Hello. Good afternoon, good morning, wherever you're hearing from. It's nice to be here once again. My name is Akerele Samuel, and today I'll be speaking on modern. I hope you can hear me, please.
As we can hear you.
Okay, please. I'll be speaking on modern deep learning approach for malware detection and classification. Before we go ahead, I would like us to look at the overview of what I have for us today, which is the background. We'll be covering the motivation and the background, overview of malware detection techniques, deep learning architecture, and data representation, also key academic contribution and current trend, case study, experimental result, and changes, challenges, and limitation. All right. In this talk, we're going to explore modern deep learning approach for malware detection and classification, and also emphasizing on the method that can integrate both automated features, learning, and domain-specific insight. Okay, so we're also going to cover recent innovation in transfer learning and assembly modeling that feature enhanced detection accuracy while reducing the reliance on extensive man feature engineering. Okay, excuse me. Okay, the overview, motivation and background. All right, the current threat landscape. So malware is becoming increasingly sophisticated and prevalent, but with zero attack posing a significant threat. And there's also need for advanced techniques, which is the traditional method. Now, the traditional method struggles to keep pace with the evolving threat, requiring scalable and automated solutions. So, why deep learning? Deep learning excel at learning complex patterns from raw data, offering a powerful approach to malware detection. Now, the overview of malware detection approach. Now, this is very critical in the aspect of cybersecurity. Now, we have the traditional approach and machine learning approach and the deep learning approach. For the traditional approach, signature-based and heuristic method rely on known data, known pattern rather, and rules, often lagging behind new threat. Signature-based detection. This approach depends on a database of unknown malware signature. That is, when a piece of software matches a signature in the database, it flags it as malicious. All right, the machine learning approach also, machine learning techniques require manual feature engineering, limiting the adaptability to a malware variant. Now, in this case, there's a support vector machine, which is a powerful and versatile machine learning algorithm, which is sometimes used for classification and regression tasks. Here, we also have the random forest, is a kind of machine that is a kind of machine learning algorithm that is known for its robustness and accuracy. The deep learning, unlike the traditional machine model, deep learning learn representation directly from raw data. This approach has been highly effective in malware detection due to the ability to handle vast amount of data. My next slide now, the deep learning architecture for malware detection. Here we have the um, convolutional neural network. I call it the CNN, the recurrent neural network, and the graph neural network. The CNN processes malware binaries as images, capturing scatter pattern and effective detection. The CNN convert binary to grayscale images to capture spatial pattern for effective detection. In this case, it optimized CNN. The accuracy of optimized CNN is actually 99%. Now, under the current neural network, also, these are type of artificial neural network. They are designed to undo sequential data, and the key feature in this network are memory, sequential processing. We have memory, we have shared memory, and also we have the autoencoder. The autoencoder are used for supervised learning. I believe my other colleagues spoke about the supervised learning. And in this case, there are two major components of this autoencoder. We have the encoder and the decoder. The work of the encoder is to compress input data into a lower dimensional representation, while the decoder restructure the original input from compressed representation. The graphic neural network models relationship between system cores. or file structure element, providing a comprehensive view of malware activity. Now, the graph actually calls for a file structure. It calls for a file structure element, providing a comprehensive view of more activities there. All right, my next slide, which is data representation in malware detection. Now, here we have the binary to image conversion. How we can convert binary to image. We have the sequential representation and the dynamic behavior data. For binary to image conversion, the malware binaries are converted into images, thereby allowing the CNN to analyze their visual pattern. Malware binaries are converted into images, allowing the CNN to analyze the visual pattern. Now, most times the binary images are converted into transforming of binary data into a visual image format. For example, the PNG, the JPG, and the BMP. This process is often used in data visualization. Now, for the sequential representation, the API calls sequential and opcode logs are used as input for RNN and the LSTMB, capturing temporal dependency. It is a concept widely used in mathematics, computer science, and also most times in data analysis and other fields. Now, this particularly is used for modeling other data like the serial, text, and DNA sequences. The dynamic data behavior collect sandbox on runtime analysis environment and provide insight into malware behavior. My next slide, which is so I have some key academic papers and contributions. You may want to take a look at these key papers probably after the event. I can just you can connect with me through my LinkedIn and other social media handle, so I can email this. So we have the academic paper and the contributions so far. Now, looking at the current trend and innovation, there's a transfer learning and also ensemble method. We have the explainable AI, right? Now, the transfer learning predefined model, the leverage for malware detection, reducing data requirement and training time. Now, in this case, model developed for one task is actually reused as a strong point for a model on a second task. Now, this approach is particularly useful when the second has limited data, and in doing so, it allows model to leverage knowledge that is learned from the first, which is data rich. And the assemble method, this method, this multiple deep learning models are combined to improve robustness and reduce bias. Now, the idea is that by aggregating the prediction of several models, the ensemble achieve better accuracy than robustness than any other single model alone. All right, explainable AI, which is XIA. The XAI frameworks are being integrated to make deep learning models more transparent and understandable. It is actually a system where it's a system that provides human understandable for that provides human understandable for their decision, or it could be prediction or behavior. And the essence of this XAI is to make AI model more transparent and interpretable, especially in the critical applications like the cybersecurity, healthcare system, and finance. Now that takes us to the case study and other experimental results. Now, leveraging LSTM and GNA for modeling detection. And the goal of this study is to was to develop a hybrid deep learning model that combines LSTM for sequences learning and GNA for synthetic data generation. We also have the train model on visual train the model on the visual shared dataset, which contains over 1 million unique malware sample. And also, the aim of this is also compare the proposed method, which is traditional machine learning, and standalone deep model. There's also the methodology used in this case. The methodology follows a multiple step pipeline. We have the data preparation, data model training and evaluation, LSTM model for data detection, and also the GNA for synthetic data augmentation. For the data preparation, the data set is to prepare is pre-processed rather using tokenization and feature extraction. And in this case, API call sequence from executable files are used as input feature. Now for data representation, all right, now getting your data ready is a cornerstone for any data-driven task. Now, here is a quick run for how the data preparation is processed. We have the data collection process, the data cleaning, data transformation, data integration, and data reduction, also data splitting. For data collection, in this case, information, it gathers all the data you need from various sources, such as a database, your web scraping, API, and even manual entries. Data cleaning involves the removal of correcting and any error in the data. This can also include dealing with missing values, outlier, and inconsistency. And I also mentioned the data transformation. The data transformation converts the data into a suitable format or structure for analysis. This involves normalization, scaling, or encoding. Yeah, for the train model and evaluation, the model are trained using Adam optimizer, which cross entropy loss function, and evaluation metrics include accuracy, precision, recall, and FAI call. Right? For training and evaluation model, training and evaluation model are actually very key steps in machine learning, and they actually have a higher level overview. The train model, it chooses for the training for model training, it chooses a model depending on it chooses a model depending on the problem, right? Depending on the problem, probably regression, classification, and clustering. You need to select a suitable machine learning algorithm. It also train test split. It divides the database, the data set into training and testing set. And commonly about 70 to 80% for training and about 20 to 30 for testing. For the model evaluation, for the evaluation aspect of it, it validates set. If you have a large enough data set, it further split the training data into training and validation set to tune your model. I also have the LSTM model for malware detection. In this case, LSTM network process sequential API call data to learn temporary dependency. And most time, this model captures patterns in how malware behaves over time. The GN synthetic data augmentation. A GN is trained to generate realistic synthetic malware samples, and also the generated samples are added to the training set. Now, there's some key findings that can justify this. Actually, model accuracy, precision, if I call. We have the standalone, and we have the GNA generated sample improved robustness, and also the real world impact. For the real world impact, it improves security. That is the real world impact of these findings. It actually improves security, and this approach provides a scalable and adaptive malware. Actually, the detect system. It can also be impactful in the aspect of adversarial defense. In this aspect, the model is more robust to evolve malware techniques and also enterprise application. It can also be deployed in the real-time data threat detection system like Google Play Store. So this is kind of useful. Now, furthermore, there are some challenges and limitations of this study. Actually, we have the adversary attack and computational resources. Adversary attack, computational resources, and also we have model interpretation, right? Model interpretability, we have the data limitation, and also response strategy. Now, for the adversary attack, the DL model can be vulnerable to careful crafted adversary examples. Take, for example, the adversary attack. These attackers measure their concerns in the field of AI, particularly in the application where security and reliability are crucial, such as autonomous driving, facial recognition, malware detection, and some attacks in the adversary aspect are evasion attacks. We have the poisoning attack and also Trojan or modern extraction. All right. The computational resources, high training and interference costs, particularly for deep network. Also, we have the model interpretability. black box nature makes it harder to explain decision to cybersecurity practitioners, and also data limitation. You have the data limitation, and also which is a scarcity of label data and the need for standard benchmark. Now, response to strategies. Response to strategies, incorporation of explainable AI and model fusion, actually. Future direction of this study, we have in the example of real-time and on device detection. So developing model can separate in the resources constrained environment, e.g., your mobile phones. In the case of cross-platform detection too, it extends solution to cover Windows, Linux, Android, and most operating system, and also the imagine of Internet of Things devices. Now it improves explainability. All right. So integration XAI framework for greater transparency and trust is automated decision, and also in the aspect of robustness to adversary attack. Now research into defense mechanism and reliance model architecture, also standardization and benchmarking. This is establishing model data set and evaluation protocol for fair comparison techniques. Now, my takeaway for this is this. In summary, rather, deep learning has revolutionized malware detection, and by automating feature extraction and handling complex data representation. And my key message for this study is transfer learning and adversary defense. Explainable AI holds significant promise for future advancement. Now, my final thought is that we need to continue to do research, collaborate between academia and industry are crucial. It's important we continue research. We need to keep doing our research. Don't stop researching, because um, there's a long way to go about this. Also, collaboration between academia and industry are crucial to address the evolving trend landscape. All right. Thank you everyone for listening for this to this short brief. I'll be ready to take any question. You can connect with me on my social media handle, McKinsey, and also my LinkedIn. Thank you. Over to you, sir.